Hello.
Hello, hello.
Okay, so let's
Okay,
start
so let's start
today's lecture.
today's lecture.
So this is
This is
mentor of
fundamental of
quantum
nano and
photonics
quantum
course.
photonics course, and
We are
we are
uh,
on
in
the
the
we are
10th
in the
week of this
10th week
course,
of this course,
and we are
and
discussing
we are
quantum
discussing the quantum
photonics.
photonics.
So in the
So
last
in the
week,
last
we
week,
talked
we
about
talked about the necessary condition
for
for
quantum nature of
quantum
light.
nature of light.
We introduced
We introduced the idea of
photon
photon
statistics,
statistics,
where we
where
described
we
Poisson
describe the Poissonian, subpoissonian, and superpoissonian nature of light.
Today we will talk
Today we will
about the
talk about
coherent
the
states.
coherent states.
So before
So
that,
before that,
just a quick
just a
revision
quick revision
uh,
uh,
regarding what
regarding what we define the second order
correlation function
correlation
and
function
its
and its
definition.
definition.
So
So
the second order
second
correlation
order
function,
correlation
that is
function,
G2,
that is G2,
is defined
is
as
defined as
expectation value
expectation value of
I at
I
t,
at time t,
the product of
the product
expectation
of expectation value of
t
time
and
t and
plus tau,
t plus tau,
and the
and the
individual
individual
product of
product
individual
of individual
expectation values.
expectation values.
Okay,
Okay,
where
where
t is the
IT is the intensity
intensity,
at time t,
tau is the
tau is the
delay,
time delay,
and
and
this bracket
this
represents
bracket
time
represents the
average
time average
expectation value.
expectation value.
So this
So
measures
this
the
measures the
so what does
so
G2
what does
do?
G2 do? G2
Measures the
measures the
correlation
correlation between
intensities at two
intensities at
times.
two times.
So so in the
So
last
in the
lecture we
last
defined
lecture we
the
defined the
uh,
uh,
we defined
we
the
defined the
experimental
experimental setup for
Brown twist
Brown twist
interferometer, that is
interferometer, that is HPT.
so we can
So we can define the
plot
plot.
here 0
Here 0
tau
tau by tau c.
at the x-axis
At the
it is tau
x-axis
by
it is
tau
tau by tau
and
c, and on the
it is
it is
G2
G2
is 1
is 1
is 2.
is 2.
So
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 when the
here
G2
when the G2 is equals to 1,
it is the
it is the
current state.
coherent state.
And when the
And
G2
when the
is
G2
greater
is
than 1,
greater than 1,
then it is
then
the
it is
chaotic
the
state.
chaotic state.
To find this,
To
we
find
saw
this,
that
we saw
this
that this
experimental
experimental
setup where the
setup
beam
where
was
the
split
beam
into
was split
two
into
parts,
two parts,
one delayed by
one
tau,
delayed by tau,
and the detectors
and the detectors will measure photocurrent
will be
that will be
proportional to
proportional to the density intensity,
the product
and
of
the product of
photocurrents will
photocurrents
give
will
the
give the
numerators.
numerators in G2.
So
So
what happens
what happens
when we have
when we have
the quantum
the
source?
quantum source?
So
So
so we have
so we have the classical.
the case
For
of the
the
class
case of the classical light
we have
cases, we have the coherent light
monochromatic
monochromatic wave,
and it will
and
give you the
it will give you the
constant intensity.
constant intensity.
No amplitude
No amplitude
fluctuations, only a
fluctuations,
phase
only
factors.
phase factors.
And the G2
And
will
the
be
G2 will be
G2.
G2 will be 1 for all tau. Means
So if the
so
G2
if
is
the
1,
G2 is 1,
means
means
there will be
there will be perfectly
uniform light,
uniform light.
means
Means
no
no
intensity
intensity
fluctuations.
fluctuations.
Coherent
Coherent
light source.
light source.
And for the
And
chaotic,
for the chaotic light, it will be
there will be
there will be
intensity
intensity
fluctuations.
fluctuations,
There will be
and there will
two
be
cases for
two cases for delay,
delay.
that is tau is greater than
Coherent time,
coherent time,
where the
where the
intensity
intensity at
T and
time t and
intensity
intensity
at time t
at
plus 2
time
will
t
be
plus 2 will be
uncorrelated.
uncorrelated.
And tau
And
is
when tau is equals to 0,
will be
it will
perfectly
be perfectly
correlated with
correlated
itself.
with itself. And
The condition
the
is
condition is
G2 at tau
G2
equals
at
to
tau
0
is
will be
equals to
greater
0 will
than
be
1.
greater than 1.
So
So,
how can we
how
understand?
can we understand this?
So suppose
So, suppose
we have
we
this.
have this system.
This is a beam,
This is a beam splitter,
a stream
a
of
stream of
photons,
photons.
here it is
Here
stop,
it is stop,
here it is start,
here it is start.
here it is.
Here D2.
These are the
These are
detectors
the
D1 and
detectors
D2.
D1 and D2.
It's a counter.
It's a counter.
Huh?
Huh?
So let's say we
So
have
let's
a
say we
stream
have
of
a
photons.
stream of photons.
E.
E.
So
So
we are considering
we are
two
considering the
sources.
two sources.
The one is
The one
bunched
is
source
bunched source,
and the other one
and
is
the other one is
coherent.
coherent source.
Okay.
Okay.
So what is
So what
happened
has happened
in the bunched
in the
source?
bunched
So
source? So
bunch
in the bunched source,
photons are
photons
bunched
are
together
bunched together
and coming in
and coming in
packets. And they're
packets,
coming.
and they're coming in packets.
Whereas
Whereas
in the coherent
in the
source,
coherent source,
average number
Average number of
of
photons are same,
but
but
but at some
but at
point
some points
photon comes
photon
random.
comes random.
So
So
fluctuations are going to
fluctuations
be
are
equal
going
to
to be
the
equal
number
to
of
the
photon,
number of photon,
delta
that is delta n is equals to
under root of
under root
n
of
bar.
n bar.
That is
That is
fluctuations will be
fluctuations
equal
will
to
be equal to the
the mean number of
mean number
photons.
of photons.
So what
So
happens
what
once
happens
when
once
a
when
stream of
a
photons?
stream of photons is incident?
So now
So now
instead of
instead of
classical
classical
brownian
Mendeleev brightness
we will
interferometer, we
consider
will
some
consider some
modification.
modification.
So now the
So
stream
now
of
the stream
photons
of
will
photons
come
will
onto the
come onto the
beam splitter,
beam splitter,
which is splitting
which
the
is
photons
splitting the
into two
photons into
parts.
two
Here
parts.
T1
Here
and
T1 and
T2
T2 are the
are the
uh,
single photon
single
detectors,
photon
which can be
detectors, which
like
can be
last
like in the
lecture we
last
saw that
lecture we
it
saw
can
that
be
it can be
photomultiplier
photomultiplier
or it
tubes
can
or
be
it can be
APDs,
APDs,
avalanche photodiode.
avalanche photodiode.
So it will
So it
generate
will generate a
one pulse.
pulse when the
So these
so
D1 and
these
D2
D1
will
and D2
generate a
will
pulse
generate a pulse
when the photon will
when the
accelerate.
photon will accelerate.
So one
So
photon
one
will generate
photon will
an
generate
electric
an
pulse
electric pulse,
and
and
so this is
so
our
this is
timing
our timing electronics
counter.
board counter.
Okay.
Okay.
So
So
whenever
wherein whenever there is a pulse on D1,
photon is coming
photon
to
is
the
coming to
detector
the detector D1,
and
and
that pulse
that
will get to
pulse will
start
get to
trigger
start
the
trigger
counter.
the
So
counter.
the counter
So
will
the
start.
counter will
So if
start.
the pulse
So
will
if the
come
pulse will
for
coming
this
for
path,
this
it will
path, it
start.
will start.
So the counter starts
Counter
counting
starts counting
how much time.
how much time.
So this
So
becomes
this
t equals to
becomes t
0.
equals to
And
0.
now
And now,
if second
if
photon
second
comes on
photon comes
D2,
on D2, it
if the other
if
photon
the other
comes on
photon
D2,
comes on D2,
it stops.
it stops.
So what
So
effectively
what
it is doing
effectively
is
it is doing is
counter will start
counter will start
measuring time
measuring
when
time
start
when
pulse is
start pulse is
generated.
generated.
Now
Now,
if another
if
pulse
another
hits
pulse
T1,
hits T1,
nothing will happen
nothing will
because
happen
counter is
because
already
counter is
started.
already started,
So
right?
it will
So
start
it will
counting
start counting
and will stop
and will
only when
stop
the
only
T2
when the
pulse will be
T2 pulse will
generated.
generated.
So we can
So we can
calculate the time
calculate the
delay
time
between
delay
these
between
pulses.
these pulses.
So let's
So
suppose
let's
first
suppose
photon is
first
coming
photon is
at
coming at
1
1
nanosecond
nanosecond,
and the next
and the
photon
next photon
comes to
comes
D2
to
at
D2 at
1.3 nanosecond
1.3 nanosecond,
1.2
1.2,
1.5.
1.5.
Delta
So
T is
delta
equals
t
to
is equals to
zero point 0.3
zero
nanosecond.
point 0.3 nanosecond.
Now again
So
if
now
pulse
again
hits
if
at
pulse hits
T1
at
and the
T1
counter
and
will
the
start
counter will
counting,
starts counting, that delta t is
the
equals
delta T
the
can be
delta
1
t can be
nanosecond.
1
That is
nanosecond. That is,
for every
for
set of
every
photons
set of photons,
there will be some
there will be
delay.
some delay.
So there is
So
delay
there is
in the
delay between
photons.
the
So when we
photons. So when
get
we
such
get
delay,
such delay,
so when we
so
get
when we
some
get
delay,
some delay,
and then we
and
can
then
build.
we can build a histogram as well.
So
So
on the x-axis
on the
there will be
x-axis, there
time
will be
interval
time interval
delta t,
delta t,
and on the
and on the
y-axis there will be
y-axis,
number
there
of
will be number of events.
okay.
Okay.
So now
So now
we saw that
show that
bunch light
bunch light
bunch light
Bunch
means
light means
the photons are
the
very
photons
close
are
to
very
each other.
close to each other.
So there are
So
time
there are
gaps where
time
there
gaps
are
where there
no
are
photons
no
for a long
photons
time
for a long time because
at
at
t time
tea
there
time there
are a lot of
a
photons
lot of
coming at a
photons
single
coming at a
time. But
single
the
time. So
next
at
time
the
there is
next time there is
lesser
lesser
probability
probability
that
that there's a high
there are no
probability that there are no
photons for a
photons
long time.
for a long time.
So coming of
So coming of
photons
photons
is a very
is
random
a very
process,
random
and there is a
process and there is equal
probability of
probability of
finding two
finding
photons
two
separated
photons
by del t.
separated by del t.
So
So
when we look at a
when we
small
look at a
time gap
small time gap
in this region,
in this region,
so when we look at
so
the
when we
small
look at the
time gap,
small time gap,
the photons
the
are
photons are
bunched. But when
bunched,
we're
but
looking at
when we are
long
looking at
time
long
interval,
time intervals,
some photons will
some
always
photons
be
will always be there
for every
for every
set of time
set of
interval.
time
That's
intervals. So
why
that's why
over a
over
long
a
time
long time
histograms
histograms
histogram becomes
histogram
flat.
become flat.
So
So
in the short
in
time
the
interval,
short time
we have
interval,
larger
we have larger
probability of finding
probability of
photons
finding photons
because
because
the photons are
the
bunched
photons are
together,
bunched together,
and for a
and
long
for a
time
long
interval,
time interval,
it becomes
it
flat.
becomes flat.
So now,
So now,
what will be the
what will be the
histogram for the
histogram
coherent
for the
line?
coherent
It
line?
was for
It
the
was for the
this histogram
this
was for the
histogram
bunch
was for
light
the bunch
source.
light source.
Now
Now
histogram for
histogram for
coherent light.
coherent light.
So the difference
So the
is that
difference is that
in case of
in case of
coherent light,
coherent light,
there will be some
there will be some
fluctuations,
fluctuations.
there are
There are
fluctuations,
fluctuations,
but the
but the
positions are random.
positions are random.
We saw that
We saw
average
that
number of
average number of
photons are
photons
same,
are same,
but the positions
but the
are random.
positions are random.
In case of
In case of
bunch light, we
bunch
will go
light, if
to
we will go to
finer
finer and
time,
finer time interval,
average number of
average number
photons
of
are higher.
photons are higher.
Suppose,
Suppose, like,
let's say
let's say
1 picosecond.
1 picosecond.
But in
But
coherent
in
case,
coherent case,
probability is
probability
constant.
is
So
constant.
average,
So
if the
average, if
probability
the
is constant,
probability is
average
constant,
number,
average number of photons is constant, and
then there is some
then there is some
randomness.
randomness.
Because of
Because of
randomness
randomness, if we
at the
look at the
correlation,
correlation,
if the first
if the
photon will
first
come,
photon will come,
the counter will
the
start.
counter will
Second
starts,
photon
and the second
comes,
photon comes,
it
it
starts.
again it starts.
We can
We
never
can
predict
never
where
predict
exactly
where
is that
exactly is that
randomness,
randomness
because like
because like
we are
we
not
we are
able
not
to
able to
locate the
locate
position.
the position.
It's very random.
It's
So
very
for
random.
any
So
set
for
of
any set
interval
of interval
delta t,
delta t,
the
the
probability of
probability of finding
photon
a
is same.
photon is same.
So
So
histogram
histogram
so histogram
so histogram will be flat
for the
for the coherent source.
okay.
Okay.
So now
So now
what
What
question
the
comes to
question comes in our mind that
can
if we can understand,
we can
we can
understand
understand
if we have
coherence if we
waves.
have waves.
Like
Like
in the last
in the
we
last
talked
class,
about
we talked about the temporal coherence and
special
the
coherence,
spatial coherence.
that is we can
That
talk
is, we
of
can talk of
fixed phase
fixed phase
relationship in
relationship
space
in space
that was defined
that was
as
defined as
coherence length.
coherence length.
That is
That is
the maximum,
the maximum.
and similarly
And similarly, the temporal
the
coherence,
maximum
the
time
maximum time
with
over which
fixed
there is a fixed
relationship
relationship,
is the
is
coherence
the
length.
coherence time.
Like we
Like
could
we could,
in
in
if we want to
if we
find
want to find out the phase
amplitude,
or amplitude, we can
we can find
we can find
exact
exact
phase if
phase
it is
if
lesser
it is lesser than the coherence
than
time,
beyond the
and
coherence
beyond the
time or
coherence time or
coherence length,
coherence
we
length,
can't.
we can't do this.
So if
So
there are waves,
if
we
there are
can
waves, we
understand.
can understand this.
But what is
But
meant
what is mean
by the coherence
by the
in the
coherence in
quantum
the
picture?
quantum picture?
So when we
So
talked
when we
about the
talked about the
statistics, we
statistics, we
photon statistics,
photon
we
statistics,
considered
we considered
perfectly
perfectly
monochromatic
monochromatic wave
with constant
with constant
intensity.
intensity.
So,
So,
but
but
there was
there
problem
was
that,
problem that
but the only thing that was considered is that the photon is unknown because the average number of photons are same. But we saw that if we keep checking in a 30 centimeter beam length or sorry because of
sorry because of some network
connection.
connection. Okay.
So now
So now
talking
we're
about
talking about
that the average
that the
number of
average
photons
number of
are same.
photons are same,
But if
but
we
if
keep
we
checking in a
keep
30
checking in a
centimeter
30
beam length
centimeter
or
beam
3
length or 3
centimeter
centimeter
or
beam length
zero point 0.1
or zero point
centimeter,
0.1 centimeter,
there will be
there will be
there will be
There will be discreteness in
of
number of photons.
okay.
Okay.
So
So
there is a
there is
possibility
a
in one
possibility
measurement
in one
we measure
measurement
three
we
photons,
measure
but
three
in the
photons,
other
but
measurement
on the
there is
other
no photon.
measurement there is no photon.
Essentially,
So
the
essentially,
discrete
the
nature of
discrete
photon is
nature of
causing
photon is causing
some fluctuations
some
in the photon
fluctuations
process.
in the photon
So because of
process.
the
So
discreteness
because of the discreteness
in number of
in
photons
number of photons
causing
causing
fluctuations,
fluctuation,
and that's why
and that's why
it's a Poissonian
it's a
process.
Poissonian process.
So now we
So
come to
now we comes to
anti-bunching.
anti-bunching. So
Anti-bunching is
anti-bunching is
where delta
where delta
is
n
to
is equals
0.
to 0.
So
So
delta
delta
is equals to
n is
0
equals to 0
implies that G2
implies
is
that
equal
G2 is
to
equals
0.
to 0.
So ideally,
So ideally,
there is a
there is a
zero count
zero count
when delay
when
between the
delay between the
detectors
detectors
is
is
0.
0.
So
So
tau
tau
G2
G2
of
of
G2 at time
G2 at
tau is
time
equal
tau
to
is
0
equals to
and
0.
tau is
At
equal
tau is equals to
to 0.
0.
So
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 ideally,
ideally,
so we can say
we
that
say
what
that
happened.
what happened.
So one more
So one
important
more
thing,
important thing,
initial days,
initial days,
we were showing the
we are showing
lasing
the lasing
characteristic by
characteristic by decreasing the by
decreasing the line,
decreasing the line width.
but it is not
But it is
necessary
not
that the line
necessary
width
that
is
if the line
decreasing,
width is decreasing,
it
then
is a coherent
it is a coherent
source. For that, we have
source.
to
For
check
that, we
G2.
have to
So if
check G2. So if
so, sometimes it's not
so
lazy;
sometimes
it's
it's
just
not
that it
lasing, it's just
amplifies
that
spontaneous
amplified
emission.
spontaneous emission.
So
So
and
and
so we talked about the quantum light
talked
cases
about
when
the
we were
quantum light
considering
cases when
photon
we were
statistics.
considering that the photon
So
statistics.
and in the
So
model, we
and in the model
modified
we modified
interferometer that is
interferometer,
the beam
that is we
splitter
placed
there.
the beam splitter
So
there. So
because of the beam splitter
because of the beam splitter
it will
detectors, it
split
will
light into
split
two
light
parts,
into two
where it
parts
will go D1
where
and
it will go
D2,
D1 and D2,
and the electronics will
and the
measure the
electronics
time
will measure the
interval
time
delta, that
interval
is the
delta, that
counter
is the counter
between the photons
between the
arriving at the
photons
two
arriving at the two
detectors,
detectors.
and then we
And
plotted the
then we plotted
histogram
the
for the
histogram for the
bunched light source
bunched light
and the
source as well
coherent
as the
source.
coherent light source.
For the bunched
For the
photons,
bunched
that we
photons, that is
talked
we
about in the
talked
previous
about in the
lecture, that is
previous lecture, that is superposition and
photon
statistics. The
tends to
photons
arrive
tends
in
to
groups,
arrive in groups,
and there is a short
and there's a short
for the short
for the short
time interval.
time
There
interval.
is a
There's a
probability of
probability of
there's a high
there's a
probability
high
of finding a
probability of
photon,
finding a photon, but
all T2 is
all
greater
T2
than
is greater
1.
than 1.
For the
But for
larger
the larger delta T,
the histogram
the
becomes
histogram
flat.
becomes flat.
So
So
high counter
high
short
counter
delay
short delays,
flatten
then
is for long
flattens for
delay.
long delays.
So for the
So for
coherent
the coherent photons,
photons arrive
photons
randomly,
arrive
but
randomly,
average
but
number is
average number
constant,
is constant,
and the
and the
fluctuations
fluctuations
come because of the
come because
discrete
of the
nature,
discrete nature,
and that is
and
delta
that is delta n
n
is equals to
the root of
under
n
root of
bar,
n bar,
and G2
and
for the
G2
coherent
for the
source is 1
coherent source is 1.
at time
At
is t
time
equals
is
to
t
tau
is
is
equals
equals to
tau
0,
is equals to 0,
and the histogram
and the
for the
histogram
coherent
for the
source is the
coherent source is
flat
the
that tells
flat,
the
that tells us the uniform
probability of
probability over all time intervals.
uniform
Uniform
probability of
probability for finding the photon.
Next is
Next is
anti-bunching.
anti-bunching.
This is the case
This
of
is the case of
subpoisonion.
subpoisonion.
Photons arrive
Photons
with
arrive
precise
with
spacing,
precise spacing,
never
never
simultaneously,
simultaneously,
and delta
and
n
delta
is
n
lesser
is
than n
lesser
bar.
than n bar.
G2 is test to
G2 is
0
test to zero
for an ideal
for an
single
ideal
photon
single
source,
photon source,
and
and
histogram
histogram
at 0 delay
depends
rises to
at
1.
zero delay rises to 1 at longer delays.
These are the key
So
points
these
that
are the key points
G2
that
provides
G2
the information about the
provides the
photon
information
correlation.
about the photon
If there is a
correlation.
classical
If there
coherent
is a
light,
classical
G2 is
coherent
equals to
light,
1.
that is G2 is equals to 1.
Classical chaotic light, G2 is
Classical
greater than
chaotic
1.
light, G2 is greater than
Quantum
1.
single photon shows
Quantum
G2 is
single
lesser than
photon
1.
shows G2 is lesser than
Coherence
1.
time and coherence,
Coherence
that
time
is
and
maximum
coherence,
interval time
that
over
is
which
maximum
fixed phase
interval time
relationship
over
exists,
which fixed phase
and
relationship
fluctuations
exists,
are
and fluctuations are
uncorrelated.
uncorrelated
Tau is greater than
when tau is
this
greater
tau c.
than this
And
tau c. And
next is
next is
coming to the quantum
coming
harmonic
to the
oscillators.
quantum harmonic
Now
oscillators.
we will
Now
consider the
we will
electromagnetic
consider the
waves.
electromagnetic waves.
We will consider the
We will consider
electromagnetic
the
waves
electromagnetic waves
as
as
harmonic oscillators.
harmonic
So
oscillators.
let's
So
consider the
let's
interaction
consider
of
the
light
interaction
with
of
matter.
light
So
with
there are
matter. So
various
there are
theories.
various theories.
So first one is
So first
classical
one is
theory.
classical theory.
According to the
So
classical
according to the
theory,
classical theory,
both matter and
both matter
electromagnetic
and
waves are
electromagnetic
classical.
waves are classical.
Picture that is follow
Picture
the
that is follow the
matter will follow the
matter will follow
Newton's
the
law, and the
Newton's
EM
law,
waves
and
are,
the EM waves are
that is it will,
that is it will
these both will
these
follow the
both
Newton.
will follow the Newtonian mechanics.
Next is
Next
semi-classical
is
theory,
semi-classical
where we
theory,
will
where
start
we will start
the
creating matter
quantum
in the
perspective,
quantum perspective,
or
or
and the EM
and the EM
electromagnetic waves.
electromagnetic waves.
So and the
So and the
waves are
waves are
treated in terms of
treated in
fields.
terms of fields.
In the
In
classical
the
and
classical and
semi-classical, again we
semi-classical,
are
again we
considering
are
the EM
considering the EM waves in
field,
terms of field,
but we will talk
but we
about
will talk
matter
about matter
as a
as
quantum
a
perspective.
quantum
That is, we
perspective.
will
That
deal
is, we
with the
will deal
energy
with the energy bands. We will treat
matter using
matter
energy
using
bands.
energy bands.
So
So
what does it
what
mean?
does
Means
it
in
mean? Means in
semi-classical, one component will
semi-classical,
be treated
one
as
component will be treated as
whereas in
quantum.
quantum
Whereas
description,
in
we will
quantum
start matter as
description,
energy
we will
bands and
start
EM
matter
waves
as energy bands, and
will
EM waves
be created
will
in
be
quantum fashion,
created in quantum
like
fashion,
photons. So
like
to
photons.
understand
So
quantum,
to understand quantum,
we understand quantum
we
harmonic
understand
oscillators.
quantum
For
harmonic
example,
oscillators. For example,
for example, a
for
pendulum.
example, a pendulum.
So here
So here,
it is a rigid
suppose it is a rigid
ball
support, and
hanging
we
by
have
a
a
string.
ball hanging by a
It will
string.
undergo the
So it will
oscillatory
undergo
motion,
the
like
oscillatory
simply
motion,
SHM,
like simply SHM,
simple harmonic
simple
motion.
harmonic motion.
So
So
here we were
here
defining
we were defining
xt is
xt
position
is position
of pendulum,
of
xt is
pendulum,
equal to
xt
x
is
naught
equals to
sine
x naught
t,
sine omega t,
momentum
whereas the momentum is defined as
mx dot is
mx
equals
dot is
to m
equals to
omega
m omega
x naught cos
x naught
omega t
cos
minus
omega
m
t, that
omega
is
p
m
naught.
omega p
These
naught,
two are
and these two are
out of
out of
phase
phase
components.
components.
So
So
and the energy is
and the
given by
energy is given by
energy is equals
energy
to
is equals to
kinetic energy
kinetic energy
plus potential
plus
energy.
potential energy.
So what is
So
happening
what is
in this
happening
case?
in this
So
case?
we saw
So
that
we saw that
there is an
there is an
interchange of
interchange of
kinetic energy.
kinetic energy, and
There is an interchange of kinetic
there is an
energy and
interchange
potential
of
energy.
kinetic energy and potential energy.
So now we want to
So now
apply
we
this
want to apply
concept.
this concept.
We want to apply
We
this
want to apply
concept
this
on the
concept
light.
on the
Light
light.
is an
So light is
electromagnetic
an
wave,
electromagnetic wave,
and we have
and
both
we have both
component, that is electric field
components, that is
component,
electric field
electric field and
component,
magnetic field.
electric field
And
and
the energy
magnetic
will
field, and
oscillate
the energy
between will oscillate
will
between
oscillate
electric and
between the
magnetic
electric and
components.
magnetic components.
Okay,
Okay,
so
so
let's consider a
let's
box which
consider a
has,
box which has,
so we can
so we
describe
can
light as a
describe
harmonic
light as a
oscillator.
harmonic oscillator.
Consider a
We'll
box which
consider a
has
box
some
which has
electric
some
field
electric
in
field
its polarized
in its
direction, that
polarized
is
direction, that is
equals to
EXZT
E
is
naught
equals
sine
to E naught sine
kz sine omega
KZ
t,
sine omega
and
t,
magnetic field is
and
P naught
magnetic field
cos
is P naught
kz
cos
cos omega
KZ
t.
cos omega t.
We know that E
We
naught
know
is
that
equal
E
to
naught is equals to BC, so B
E
naught
naught
is equals
by
to E
C,
naught by C.
and what is the
And
energy
what is the
density
energy
is given by
density is
half
given by
epsilon
half
naught
epsilon
square
naught E square
plus B square by
plus
2.
B square by 2 mu.
So now we
So
want to
now we want to calculate,
now we want to
now we want
calculate
to calculate
how much
how much
amount of energy,
amount of energy,
how much amount
how
of
much amount
energy
of
is
energy is
present
present
in electric
in electric
component.
component.
Okay,
Okay,
so
so
that
for that
E
E
electric
electric
is equals to
is equals to half
not
epsilon naught
area,
area,
and we will
and we
integrate
will
over
integrate
0 to
over
2.
0 to L.
This is the box
This is the box
dimension.
dimension.
E naught
E naught square
sine square
sine
k
square kz
sine square omega
sine
t
square omega t
dz.
dz.
So it will give
So
us
it will give us half
epsilon naught a
epsilon naught a
e square
E naught square
sine square
sine
omega
square
t, and the
omega t, and the integration between
integration will be of
integration
sine
will be
square
of
kz.
sine
So
square
sine square
kz. So
kz we
sine
can
square
define
kz we can
1
define
minus 2 kz
1 minus cos 2 kz
by 2 dz,
by 2
which will
dz.
give
So it
us
will give us
4
1 by 4
not v, where v
epsilon
is
naught
equals
v,
to
where v is equals to
area into length
area
volume.
into length
So
volume.
electric
So
field का whole
electric
square
field का whole square
sine square.
sine square.
Hmm. So this is the
So this
amount
is
of
the
electric
amount of
energy.
electric energy.
Similarly, we can find
Similarly, we
out
find
the E magnetic,
E magnetic,
which is 1
which
by
is
4
1 by 4
volume
volume
V naught
V
square
naught square
upon mu naught
upon mu naught
cos square
cos
omega t.
square omega t.
And the total
And the
energy
total
density
energy density
given
between
by
given by
E is equals
A
to
is equals to
E total
E total
equals
is
to
equals to
E total
E total
E total
E
equals
total
to
equals to
the sum of the electric
The sum of
energy
the electric
plus
energy
magnetic energy. So
plus magnetic energy. So V by 4
epsilon naught
epsilon
E
naught
square
E square
sine square omega t plus
sine
B
square omega t plus B square
cos square omega t.
cos
So
square omega
from
t.
this
So
we can
from
say
this we can say that
the energy
the
oscillates
energy
between
oscillates
electric and
between
magnetic
electric
field.
and magnetic field.
So now we
So
don't
now
want to
we don't
deal with
want to deal
electric and
with
magnetic
electric
field
and magnetic
directly.
field
So
directly. So
we will make an
we will make
analogy
an
to
analogy
simple
to
harmonic
simple
motion.
harmonic motion.
So we
So
will
we
introduce
will
the
introduce the
generalized coordinate.
generalized
So
coordinates. So
electromagnetic wave have no
electromagnetic wave
mass,
have
so
no mass, so
cannot
we
directly
cannot
use
directly
classical
use
oscillator
classical
variables.
oscillator variables.
So we will
So we
introduce
will introduce the
we will
we
introduce
will
the
introduce the
generalized coordinates
generalized
QT
coordinates
and
QT and PT
analogous to X
analogous to
in
X and P
classical
in classical
oscillators,
oscillators,
and where we were
and where we were
the
defining
energy
the
E is
energy
equals
E
to
is
half
equals to
omega
half
square Q
omega
square.
square Q square plus P
How
square.
did we derive?
How did we derive?
How can we derive?
How can we derive it? So
We have the total
we
energy.
have the total energy. So
Define it
we
as
will
the generalized
define the
coordinate.
generalized coordinates QT
QT is equals
QT
to
is equals to
epsilon naught V
epsilon naught V
upon 2
upon 2 omega square
1 by 2
1 by 2
naught
E
sine
naught
omega t.
sine omega t.
We can define
We can
it
define
as
it
X.
as X.
Similarly,
Similarly, PT
V by 2
V by 2 mu naught
Px by root
Px by root m.
omega square
Omega square
t
Q square T
is equals to
is
epsilon
equals to epsilon T
2 omega
2
square
omega square
q square
Q
omega
square
square
omega
naught
square
sin
E
omega t.
naught sin omega T.
So
First term,
the first term in the
the
total
first term in
energy
the total energy
is half of
is
electric.
half of electric.
So half of
So
electric
half
is
of
epsilon
electric is
v
epsilon naught V
e naught sin omega
E
t
naught
by 2.
sin omega T by 2.
Similarly, p square
Similarly, P
equals
square
to v by 2 e naught
V by 2
half
knows
e
that is
magnitude.
half E
Is
magnetics
equals to
is equals to
half omega
half
square q
omega square Q square plus
p square.
P square.
Since we know that
Since we know that
b naught
B naught
square e naught
square
square
E
by
naught
c
square
square,
by C square,
we can write
we
it
can write as mu
epsilon
naught epsilon naught
e square.
E square.
So if we want to
So if we
find
want to find out the total
that
energy,
is v by
that is V
4
by 4
epsilon naught e
epsilon
naught
naught E
square
naught square
sin square
sin
omega
square
t
omega
plus
t
mu naught
plus mu naught
naught
epsilon
e
naught
naught square
E naught square
cos square omega
cos
t
square omega
by
t
mu naught
by mu naught
is equals to
is
v by
equals to
4
V by 4
epsilon naught e naught.
epsilon naught E naught square.
So we can
So we
represent.
can represent it.
So this is the
So
total
this is the
energy
total energy which we can
write in either
write
terms
in
of
either
electric
terms of
field or in
electric field
terms of
or
the
in terms
magnetic
of the
field.
magnetic field.
So now
So
we can
now we can
represent
represent
just like
just like we
saw in the high
saw in the
school
high
that
school
we can
that we
represent
can
the SHM
represent the SHM
on
in,
the phasor
on the
diagram.
phasor
Similarly,
diagram.
we can
Similarly, we can also represent the
we can
we
represent
can
in
represent
terms of a
in terms of
phasor
a
diagram.
phasor.
So ext
So ext is equals to,
so
so
let's
first
see how
let's see how can we represent.
this is
This
imaginary
imaginary
absolute.
absolute. So
Ext
ext
is equals to e
is equals to e naught
sine kz
sine kz
sine omega t,
sine omega t. So
and
and
generalized phase.
generalized phase omega t plus
So
phi.
this is, we can,
So this is, we can,
using the formula of
using the formula of sin a plus b sin a
cos p
cos b
plus cos a,
plus cos a sin b.
so we can write it
So we can write it, separate it into two parts,
as
and we can write as
1 cos
e1 cos phi
plus e2
plus
sin.
e2 sin phi.
We can generally
We can generally write it e naught
e out of it.
e.
So now,
So now,
what are the phase
what are the phase diagrams and the field diagrams?
So we can write it in terms
It
of,
is so,
there are field
there are
packages,
field
so we
packages, so
represent
we are representing the
electromagnetic wave
electromagnetic
in
waves
terms of
in
phase.
terms of phasor.
That is,
That is,
we will represent
we
the
will
vectors in
represent the
complex
vectors in
plane, and
complex
we will
plane, and we
introduce
will
the field
introduce the
curvature
field
section,
curvature section next to,
which will be out of
which will be out
phase.
of phase by Fibonacci.
So since
So
x1 is
since
sin
x1 is
t,
sin omega t and
cos
x2 is cos omega t.
so just
So
like
just
we were
like
represent,
we were representing the real and imaginary part,
we will
we
represent
will represent
x1
x1
and x2.
and x2.
Epsilon naught v
Epsilon naught v upon
4h cross
4h cross omega
half
half
naught.
a naught.
So we can define it.
So we can define it.
So this is our x1
So
t.
this is our x1t.
What are these
So
quadratures?
what are these quadratures
Quadratures
helping? So
essentially are the
quadratures
components
essentially are the
which are
components
separated by a phase
which
of
are
pi by
separated
2.
by a phase of pi
These
by
are
2.
called
and
feed
these are
quadratures,
called
and it will
feed quadratures,
simply
and it will simply
quadratures simplify
quadratures
visualization
simplify
and
visualization and analysis of
on the
electric
same
and
scale.
magnetic field on the
So
same
x1
scale.
t is
So
equals to
x1 t is equals to
epsilon naught v
epsilon naught v
sin omega t
sin omega t
v naught cos
E naught cos
we can
omega t.
write it
We can write it omega by 2h cross
half
half
qt.
qt.
Similarly,
Similarly,
1 by 2
1 by 2 h
omega
cross omega
half
half
t.
pt.
So that
So
means
that
it
means
represents
it is representing
the electric
the
energy
electric energy or magnetic energy
by h cross
by h
omega
cross omega
t.
1 by t.
This is
So
energy,
this is energy
and this is also
and
the
this is
energy.
also the energy.
Energy
So
divided by
energy
energy.
divided by energy. So
These
H1
are
and
the
H2 are the
dimensionless,
dimensionless
dimensionless
dimensionless quantity,
and
and
x1
x1
square
square
plus x2
plus
square
x2
will
square
give you
will give you
epsilon naught
epsilon naught v
4h cross
4h cross omega
naught
v naught square
omega square
omega
t
square ct
by 2h
by 2h cross
p square,
p square,
which will give you
which will give you h cross omega.
so this is the case
This is the case where we are representing.
we considered
We considered
to understand
to
the quantum
understand the
nature
quantum nature. We understood electromagnetic waves
as fields
as fields
and matter as
and
a
matter as a
bands,
bands,
quantum fashion,
quantum fashion, and
we representing the
we representing
quadrature
the
in terms
quadrature in terms of
of
electric
field.
and magnetic
So
field.
now, if
So
we are
now,
considering
if we are
light as a
considering
quantum
light as a quantum
oscillators,
harmonic
so
oscillators,
we will
so
introduce a
we will
very
introduce a very
fascinating idea in
fascinating
quantum
idea
optics.
in quantum optics.
That is
That is
vacuum field.
vacuum field.
Okay.
Okay.
So
So
for this, we will start
for
with
this,
the
we will
treatment of
start with
light
the treatment
as
of
a
light
quantum
as an
harmonic
quantum
oscillator.
harmonic
So the
oscillator.
energy
So the
of the
energy of the
quantum harmonic oscillator
quantum harmonic oscillator is given by n
1 by
plus
2 h cross.
1 by 2 h cross omega.
So if
So
we have a
if we
single
have a single
photon,
photon,
then classically
then classically
classically
so
the energy is
classically the
given
energy
by
is given by
number of photons
number of photons into h cross omega,
and quantum
and
mechanically it
quantum
is
mechanically it
n
is
plus
given by n plus half h
half.
cross omega, where n is number of photons.
So if we have
So if we have a single number of single photon,
then classically
then
that
classically the
will
energy
be
will
h
be
cross omega.
h cross omega, whereas
Quantum mechanically
quantum mechanically we will have the 1.5.
if we are having the
If we
10
are having the 10 number of photons,
then the classical
then the
is
classical it is
10 h cross
10 h
omega
cross omega,
and quantum
and
mechanical
quantum
is
mechanically it is
10.
10.5.
But if we
But
have
if we have
thousand
the
number of
1000 number of photon, then
there is no
there is no change
in energy
in
of
energy of
classical and
classical and quantum
harmonic oscillator.
harmonic oscillator.
So what
So
it
what
says
it
is
says is,
as the number
as the number of photons
increases,
increases,
as the number of
as the number of
increases,
photons
the
increases, the classical and
picture
quantum picture
is the
gives
same
the same.
as the number of
As the number
photons
of photons
increases. The
increases, the
classical and quantum
classical and quantum
is the
picture gives
same.
the same
But the
energy.
moment
But the moment we
go in few
go
photons
in
present,
few
that we
photons
saw in
present, that is
one
we
photon,
saw in
three
one
photons,
photon or three
then there
photons,
is a
then
change
there is a
or
change
divergence between
or
classical and quantum
divergence
energy.
between classical and quantum description.
So let's consider
So
the
let's
quadrature
consider
to
the
understand
quadrature
this. So
to
first of all,
understand
we
this.
have
So
to
first of
calculate
all,
the
we have to
uncertainty
calculate the
delta
uncertainty
x1.
in delta x1.
So what will be
So
delta x1?
what will be delta
So
x1?
delta x1 will be
Delta x1 will be
omega by 2 cross
omega by 2 cross
delta q
delta q.
delta x2 is
Delta
equals
x2
to
is equals to
1 by 2
1 by 2 h cross omega
1 by 2
1
delta
by 2
p.
delta p.
So
So delta x1
delta x2
delta
will be
x2 will be omega by
2 cross
2 cross into 1 by 2
omega
cross omega
1 by 2
1 by 2
delta q.
delta q and delta p.
So
So
know that
we know that delta q we have represented.
delta q
Delta
is
q is
root m delta
root m delta x.
delta p
Delta p
delta
is delta
root m
root m.
1 by
1 by 2
cross
cross
delta m.
delta m delta p.
So we know that
So we know that delta x,
product of
the
delta
product of delta x and delta p gives us h cross by 2.
so 1 by
So 1 by
h cross
2 cross,
it is given
it is give us 1 by 4.
that is
That is
delta x1
delta x1
delta
delta x2
is greater
is
than equal
greater
to
than
1.
equal to 1 by 4.
And we saw that
And we saw
in
that
this case
in
there is
this
no
case there is no h cross.
because
Why? Because we saw
x
that x1 and x2 are the dimensionless
so this is
quantity. So there is no meaning of h cut.
so now
So now
the
the
so what we said
so what we say that we have
x1 and x2 and
x1
we
and
define
x2 and we define uncertainties
them
for
delta
them delta x1 and delta 2 using the generalized coordinates
q.
of p and q.
We found the
We
product
found the product of uncertainties
delta x1 and
delta x1 and delta x2.
1 by 4.
1 by 4.
This is exactly similar
And this
to
is exactly
Heisenberg
similar to the
principle,
Heisenberg
but for
uncertainty principle, but for
dimensionless field curvature.
dimensionless field
So
curvature.
physically, this means
So
that
physically, this
magnitude
means
and phase
that
of the
magnitude and phase of the
wave we
electromagnetic
cannot
wave we
precisely
cannot precisely
non-simultaneously.
non-simultaneously.
So in a phasor
So in a
diagram,
phasor diagram,
x
x1
is one
x is
quadrature,
one
x2
quadrature, x2
is
x
another
is
quadrature,
another quadrature,
and we can
as we
define
can
x1 and
x1
x2.
and x2.
So here
So here
shaded region
shaded region
will give the
will give the reason of
uncertainty
uncertainty
in
in
electromagnetic wave,
electromagnetic wave,
assuming
assuming
delta x
delta x1
and delta x2 is
and
equals.
delta x2 is equals.
So if we have a
So if
classical
we have a
wave
classical
with
wave
large
with
electric
large
field, this
electric field, then this
uncertainty will be very
uncertainty
small.
will be
That
very small. That is
is delta x by
delta
x1
x
is
one by
equals to
x1
delta
is equals
x2
to
by
delta
x2 is very
x2 by
less
x2 is
than
very
1.
very less
But
than
for large
1. But
power
for large
lasers,
power
since
lasers,
if we are
since
considering
if
the
we are
large power,
considering the large power,
there will be no
there will be no
uncertainty
uncertainty, and for a few photon,
uncertainty have to
uncertainty have to be
be considered.
considered.
So for vacuum
For
field,
vacuum field,
for n is
for
equals
n
to
is equals to 0,
E naught is
E
equals to
naught is
half
equals to half h
omega.
cross omega.
What is this
What
saying?
is it saying that?
So what is this
So
saying?
what is this saying that? It's saying that
If we
if
have
we
no
have
photon,
no photon,
if we have no
if we have
photon,
no
then
photon,
also
then also
we have some
we have
energy.
some
So
energy.
E
So E
energy is not
energy
equals
is
to
not
zero
equals to 0
with no photon.
with no photons.
Suppose
Suppose
that is we can.
that is we can.
So suppose we
So
are
suppose
considering consider vacuum where
we are
there is no
considered
photon,
vacuum
but
where there is no
even then
photon,
there
but
is some
even then
energy
there is some
that
energy
we call the
that we
0
call
point
the
energy.
0 point energy.
So
So
so suppose if
so
we
suppose
have
if
H
we have
cross
h cross
omega
omega
is equals to 2 electron volt is
electron
very
volt
greater than the thermal
is
energy
very
of
greater than the thermal
5
energy, which is of the order of 25
So when
milli
we have
electron
such
volt.
scenarios
So when
at
we
that
have such
particular
scenarios
lambda,
at that particular lambda,
what will be the 0 point energy?
what will be
If
the
we
zero
know the
point
zero
energy?
point
So if we
energy,
know
we
the
know
zero
the
point
amount of
energy, we
energy
know the
stored in
amount
the
of
electric
energy
field and
stored in
vice
the
versa.
electric field and vice versa.
So
So
half H cross
half h
omega
cross omega
is equals to
is
2
equals to 2 into 1 by 2
volume
volume
epsilon naught
epsilon naught
square
E
vacuum
square
is equals
vacuum
to
is
epsilon
equals to
naught
epsilon naught
T square
E square
vacuum.
vacuum.
That too is
So
because
that too
of
is
the
because of the
magnetic field
magnetic
contribution.
field contribution.
So we know
We
that
know that
vacuum
E
is equals
vacuum
to
is equals to
cos
h
omega by
cross omega by
2 epsilon naught
2
V.
epsilon naught
So
V.
this is
So
the
this
even we
is the
have
even we have vacuum.
this is the
This
electric
is the
the
electric field.
certain
There is a certain
amount of
electric
electric field
amount of
and
electric
this is
field, and
called the
this is called the
vacuum field.
vacuum field fluctuations.
So when we have
So when we have a
electromagnetic
classical
field, there is
electromagnetic
no
field,
field,
there is
nothing,
no
but
field, nothing. But
here in vacuum
here in
there are
vacuum,
no
if there are
photons
no photons,
has certain
has
amount of
certain amount of
fluctuations.
fluctuations.
So what is
So
vacuum
what is
field?
vacuum
Consider
field?
case and
Consider
equals to
case n
zero
equals to
photon,
0 photon, E naught
one
is
by
equals to
two,
1 by
even with
2,
no
even with
photons,
no
energy is
photons,
at energy is not zero.
energy is not
This was
0.
zero
This
point
was 0
energy.
point energy.
And if there is
And
no
there is
field,
no
then also
field,
we
then
have
also
some
we have
field
some
which is called
field
the
which is called the
vacuum
vacuum
fluctuations.
fluctuations.
So
So
we will take the
we will take the 10
after
minutes
that
break.
we will
After that,
proceed.
we will resume.
Okay, so
Okay,
let's
so
start
let's start
with the example.
with the example. So we want to calculate the magnitude of vacuum fill
Cavity.
in a cavity of
Vacuum
vacuum fill 1 cube
at
at 500 nanometer.
so
So
E vacuum
E vacuum
will be
will be given by
H.
H cross omega to epsilon naught V.
So we
So we can calculate the energy
is
is 1.24,
0.5.
0.5.
It will
It will give you 2.48 electron.
just
Just plug in the values of H omega,
an
and
absolute
epsilon is 8.85 into 10 to the minus
12.
12.
We will
We will get the
4.7.
4.7 volt per meter.
Okay,
Okay,
and
and
so
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 E
E
vacuum
vacuum
is
is proportional to 1 by cavity volume V.
B
B
part
part,
if
if
one
1 micrometers,
if we
if
have
we have the 1 micrometer
tube
tube cavity
wall.
volume, that is 10 raised to power minus 18 meter cube.
So
So if we will calculate the
E
E vacuum, electric field in vacuum, it will give us the
vacuum
1.5 into 10 raised to power 5
volume.
volume per meter.
So that
So that is,
it's
it's
very
very large
electric
electric
field.
field
And
when volume is small.
so
So we can conclude that
small
small cavity
will
will give you the
large
large vacuum electric field fluctuations.
that
That implies the strong spontaneous emission. and which implies if the spontaneous emission is strong, then the fluorescence lifetime becomes very very small.
So
So
now
now we will define the coherent states and
squeeze.
squeeze states.
So
So
coherent
coherent
state
state
is a
is a quantum mechanical analogy
of
of a simple monochromatic wave.
this
This is the so we consider the monochromatic
wave.
wave is the purest form of waves and can construct any object out of various monochromatic waves.
Just
Just like a pure sine wave is a classical physics, a coherent state is pure in the quantum sense.
so
So,
how
how did we represent it? So, we represented it as
coherent
coherent
can
states. We can represent, we saw that
the
we can represent the coherent state in the quadrature space,
that is
that is x1 and x2.
so
So,
and
and we define the alpha
is
is equals to x1
plus
plus iota x2 iota, because this was out of phase by pi by 2.
the
So alpha is also
element
dimensionless quantity, since x1 and x2 are
so according to
dimensionless.
the Fermi
So
Golden
according to the Fermi golden rules, we know that
transition from
transition from
initial state
initial state to
final state
final state,
integration
integration over volume,
state
state,
final
final
state
state,
x
x,
initial
initial state,
and
and alpha.
this
This will give us the magnitude of phasor, phasor magnitude,
steps
epsilon naught b
4
4 h cross omega.
so
So what? How can we understand the?
how can
How can we
physics
physical?
how can
How can we understand the physical interpretation? So that is magnitude of coherent states means. So classical energy.
so
So
class
classically,
the
the
energy
energy,
classical
classical energy
is
is 1 by 4 epsilon naught b
you know
e naught square.
that is
That is equal in terms of phasor h cross omega. For photons
is it
is equals to n h cross omega,
and
and alpha is equals to under root n bar.
so it
So it means
the
the
length
length of phasor.
so this
So this length of phasor
is
is be
proportion
proportional to the mean number of photons.
so
So
different
difference in delta n
is it
is equals to alpha plus 1 by 4
okay,
ka
square
square minus.
so
So
this
this difference
in the
in the phasor length represents the uncertainty.
that
That is alpha
is
is
equals to
equals to under root n.
so
So
coherent
coherent
state
states exhibit
minimum
minimum uncertainty,
and
and
that's
that's why in
point
Poisson statistic, therefore delta n is
to
equals to
mean number
mean number of
we
photons. So
can
we
talk
can talk about alpha as magnitude and phase, that is
alpha
alpha e iota phi.
and this
And this phase also exhibits an
uncertainty
uncertainty relation,
that is
that is we can define in arc length
is it
is equals to
under
under root n bar, delta phi is equals to 1 by 2
just
Just
similar
similar delta n,
delta
delta phi,
by
1 by 2
for a
for a coherent state.
so this
So this is the number phase uncertainty relation. If we have a large number of photons,
so if
so if the photon number is large, delta n is large, but delta phi is small, so
phase
phase is well defined. In reverse case, if photon number is small, then
phase is
phase is poorly defined.
so
So
coherent,
coherent state follow the Poissonian statistics,
but
but
we saw
we saw physical interpretation
that
that in a few photon regime, delta n is small, delta phi is large,
and
and
as the
as the number of photons increases,
relative
relative
fluctuation
fluctuation, that is delta n by n bar,
that
that decreases and the wave becomes well defined,
and
and delta n and delta phi is
great
greater than 1 by 2.
and
So as n increases, delta n
increases
increases, delta phi decreases,
and the
and the
vice
vice
versa.
versa.
So
The reason around the phasor represents
the
the reason around the phasor represents
uncertainty.
uncertainty in the amplitude and phase.
So as
So as the photon number increases, quantum fluctuation reduce relative to the mean, approaching classical wave behavior.
so now
So now we will solve an example.
we are
We are considering a coherent state
with
with
alpha
alpha
is
is
equals to
equals to
pi.
pi.
So we
So we want to
calculate
calculate
mean
mean photon number.
second
Second, we want to calculate the standard deviation.
and
And third, we want to the quantum uncertainty.
the
In the optical phase.
so
So
first
first is mean photon number.
since
Since it is
so we
so we saw that the length of the phasor, that is
and
alpha square is equals to n bar. So it is,
so if
so if alpha is equals to 5, n bar is
to
equals to n
20
25.
b
B,
the
the
standard
standard deviation in photon number, that is delta h. So since it's a coherent
state
states exhibit Poissonian statistics,
that
delta n is equals to n bar
5
5.
and
And then C, uncertainty,
that
delta n,
delta
delta phi is
was
equals to
1
1 by 2.
so
So delta phi is equals to 1 by 2 into 5.
that
That is 0.1 radians.
so
So
suppose
suppose if we have
10
10,000 photons,
delta
delta phi is equals to 1 by,
and
and bar is equals to 10,000, and delta phi is equals to 1 by 200. That is 0.005.
that is
That is
uncertainty
uncertainty's
is
phase decreases. So as the
and
n bar increase, number of photons increases, delta phi decreases.
so next
So next is squeeze states.
so
So squeeze states are quantum states where the uncertainty
in one
in one quadrant is reduced
below
below the coherent state limit at the
expense
expense of the other.
so
So
what does
what
this
does this mean? So
suppose
suppose
early
earlier we have this quadrature.
the
So these are the vacuum states.
Here,
Here now
delta
delta x1 is lesser than 1 by 2. Delta x2 is greater than 1 by 2.
two,
So
you can
you can
see
see
x1,
x1,
x
x2.
along
Along the
two,
x2, the uncertainty is increased,
and
and
x1,
x1 along the x1 uncertainty is decreased.
so
So
that
that
it's
it's
not
not
case
case
that
that the reason of uncertainty
will
will be
all
always
circle.
circle.
So,
So
so
in quadrature uncertainty, if there is a coherent state,
then the
then there will be
delta
delta x1 is equal will be equal to delta x2, and that will be equals to
one,
1 by 2.
but it
But in
so
case of
squeezing.
squeezing,
So
if
if
there is a
there is
phase
a
squeeze
state, then
state, then
delta
delta pi
less
is
than
lesser
1
than
by
1 by
the
2, and the delta n is
greater than
greater
1
than
by
1 by 2.
if it is
If it is an
a
amplitude squeeze
then
state, then
delta pi
delta
will
pi
be
will be
greater
greater than 1
than
by 2, and
delta
delta n is lesser than 1 by 2.
it means
It means
the
the
product
product of
delta
delta
x1
x1
delta
and delta x2
is
is
greater
greater than 1 by 4.
so it
So it
leads
leads to
the
the
squeeze state
squeeze state. That is, we are reducing the uncertainty in one of the axes.
so the
So the uncertainty
ellipse shows
ellipses show where the phasor can lie.
unlike
Unlike coherent state, one uncertainty is
squeeze
squeezed to improve
measurement
measurement
precision.
precision along that axis.
So
So
energy of
energy of
light
light.
what
So what
we
we
studied today
studied
that
today, that is
is
energy of light is
quantized
quantized. Classical and quantum energies match for a large number of photons, differ for few photons.
field
Field
quadratures
quadratures x1 and x2 have an uncertainty relation, that is delta x1
delta x
into delta
is
x2
greater
is
than
greater than 1 by 4. 4.
this
This
uncertainty
uncertainty implies uncertainty in magnitude and phase of the magnetic field.
then
Then
vacuum field
vacuum field, that even with no photon, there are electric field
fluctuations
fluctuations,
for
and for smaller cavity volumes, there are strong
vacuum field
vacuum field
that will
that will
imply the
imply the enhanced
spontaneous
spontaneous emission.
then
Then these concepts are
central
central to the quantum optics and helps
explain
explain phenomena like
particle
Purcell
effect
effect.
then we
Then we study about the coherent state and squeeze state. So now coming to the assignment.
so the
So
first
the first question is temporal coherence manifests itself
as
as.
so we
So we
studied
studied about
temporal
temporal and
special
spatial coherence. So temporal
uh,
uh,
coherence
coherence manifests itself as a.
what does it
What did we saw?
we saw
We saw in the previous
that
lecture that
temp so
so
temporal
temporal coherence
tells
tells about the
line
line width,
that is
that is spectral width.
so
So
if the
if it is telling about us about the
with
spectral width of light,
then
and it will tell us
about the
about the
monochromaticity of light
monochromaticity of
temporal
light.
coherence
So
tells us
temporal coherence tells us the
monochromaticity
degree of
and
monochromaticity
the spectrum
and the spectral width.
next
Next
the
is the visibility of fringes in
young
Young's
double slit
double slit
experiment
experiment in the
manifestation
manifestation of
statistical
statistical nature,
quantum
quantum
nature
nature,
spatial
spatial
coherence
coherence, or
temporal
temporal coherence.
so
So
spatial
spatial coherence
tells
tells us
how
how well the phase of the wavefront are correlated
across
across different
in
points in
space.
space.
So
So we saw that in Young's
double slit
double slit
experiment
experiment,
there
there
were
were
two
two
slates
slates
and
And
these
these
two
two
act
slit act as two secondary coherent sources
like
like this.
and
And
for
for
stable
stable and high contrast
fringe, the
fringes, the
light
light reaches
reaches
to
to
the
the
both
slits
slits
must have
must have a
fixed
fixed
phase.
phase relationship.
So there
So there was condition of
was
uh,
happening
happening. The interference
there
was if
should
there
be
should be monochromatic
wave,
wave,
constant
constant
phase.
phase amplitude.
So if
So if the source is
this
extended, that is not point like the different parts of source will eliminate
the slit
the slits with highly
slightly
slightly different phases. So that will reduce the correlation between the two slits,
and it
and it will not lead
the
to the
interference
interference, and this will reduce the
visibility.
visibility.
So this
So this
reduction
reduction
lowers
lowers the
the
fringe
visibility.
visibility.
So the
So the visibility is related to the
special
spatial
coherence.
coherence.
On the
On the other hand, the
temporal
temporal
coherence
coherence
decides
decides
how many
how many fringes are available
across the
across the
screen.
screen.
That is
That is the fringe length or coherence. But
special
spatial
coherence
coherence
decides
decides whether the fringes are visible
or
or not.
so
So
the
the
next
next
question is
question
the
is the
delay
delay
over
over
which the
which the
correlation
correlation in
phase or
phase or
amplitude
amplitude
of a wave
of a
decreases by
wave
a
decreases
significant
by a
amount is
significant
defined
amount
as
is defined as
coherence time,
coherence time,
coherence length,
coherence length,
pulse width,
pulse width,
wavelength of the
wavelength
light,
of the
or
light, or
coherence.
coherence area.
So we
So we
know that
know that
if there is a
if there is a
delay
delay
beyond
beyond
a
a
coherence
coherence
time,
time, we cannot
we
detect
can tell that
tell the
what is
what is
the
the
phase.
phase or amplitude.
So the
So the
answer
correct
is
answer is
coherence
coherence
time.
time.
These are
These all we saw in the lecture.
so the
So
next
the next
question is
question is
consider the
consider the
following
following
sources with
sources with
corresponding
corresponding
coherence
coherence
time.
time.
Choose the
Choose the
correct
correct
option. So
option. So
first is
first is LED
for that
for
the
that the
delta
delta
lambda is
lambda is
50
50
nanometers.
nanometers.
Then is
Then is
tungsten
tungsten
filament that
filament that
for that
for
delta
that delta
lambda is
lambda is
100
600
nanometers.
nanometers.
Then
Then
sun
sun
delta
delta
lambda is
lambda is
1
1
mm.
mm.
And
And
then
then
laser
laser
for the
for
delta
the delta
lambda
lambda is
is
equals to
5
5
nanometers.
nanometer.
So
So
we know
we
that
know that
coherence
coherence
time
time tau
is
c is
inversely
inversely proportional to 1 by delta lambda.
right.
Right?
So
So
among these
among these
options,
options,
first
first is
lambda
lambda
for
is
sun
for sun
is
is
very
very large.
so
So
delta
delta lambda
3,
3,
then
then delta lambda
2,
2,
then
then delta lambda 1,
and
and then delta lambda 4.
so
So
if the
if the
if
if
if the
if the
delta
delta lambda is large, then the coherence time will be less. So
for the
for the
sun
sun, the coherence time
will be
will be
the
the
least,
least.
then
Then for
2
2,
C
C1,
C
C4.
so the
So the correct answer is
C
C
3
3, C2, C, and C.
the
The correct mathematical
expression
expression for the second order correlation function G2 is
I
IP,
into
intensity at time T, intensity at time at O.
the
The
correct
correct
answer
answer
is option.
is option 5.
Next
Next
question.
question, light is said to be bunched if
Just
just right now we saw that
like
the light
according
according to the G2 condition, the light will be bunched if
to
J2 at time tau
is
is
greater
greater than
than
J2 at
zero.
time 0.
Option A
Option A.
and
And anti-bunched
if
if
G2
G2 at time tau is greater than
G2
G2 of 0.
option.
Option A.
Then the
Then the classical
classical
Hanbury
brown
Brown twist interferometer exhibit.
What
What does it do?
we saw
We
that
saw
it
that it
is a
measures the
cross
cross
correlation
correlation between
photocurrent.
photocurrent.
So the
So the
option
option
P.
P.
Next is
Next
for
is
a
for a given
monochromatic
monochromatic
light
light
wave
wave with a
constant
constant intensity A naught,
value
the value of
G2
G2
is
is
G2
G2 at time 0.
so we
So we saw that G2 0 is
I
IT,
I
IT plus tau,
I
IT,
I
IT plus tau.
now
So now time is 0. So it will be 0. So it will be
I
I
square
square T
divided
divided by
I
IT square.
so we
So we know.
so
So we know that.
so we know
So we know that it is given that
P is
IT is
equals to
equals
A
to A naught
for all
for all T.
IT is
IT is equals to A naught
I
IT
squared
square T is equals to A naught
here.
square.
So
So G2
0
0 is equals to A naught square by
and
A naught square. It is 1.
the
So the correct answer is
for a
for a given light, if it is a constant intensity,
then
then
the
the
G2
G2 is
one.
1.
Next
Next question is
calculate the
calculate the value of
for
G2
a
for a monochromatic light
with a
wave with a
square
square wave intensity modulation of
plus
plus minus 20%.
so
So
just from
just from the previous question,
G2
G2 is equals to 0,
is
I square T,
right.
I T square.
So
So earlier it was constant intensity, that was IT is equals to A naught. So
now
now
it
it
has
has plus minus 20%. So
1.20%
IT is equals to
1.0
1.2 I naught, 0.8 I naught.
okay.
Okay.
So
So
how
how now we can write
I
IT
is equal
is equals to
to 1
1.2 I naught
plus
plus
0
0.8 I naught
by 2
by 2.
that
That will give me.
so how
So how
this is the
this is a value of
IT.
IT.
Now
Now
I
I square
T
T
which is
which is
1
1.2 I naught
square
square plus
8
0.8 I naught square
upon
upon 2,
which
which
is
is
1
1.44
I naught
I naught square
0
0.64 I naught square
by
by 2 2.08 I naught square
by
by 2, that is
1.
1.04 I naught square.
Now
Now we can find, if I have the value of
expect
expectation of value of I square t, we can find the value of G2.
so
So
that
that is I square 2,
that
that is 1.04 I naught square, and IT
is
is I naught square,
this
that is 1.04.
option.
Option A is correct.
Next
Next question is,
is
a
your
source emits a train of single photons with exactly regular time intervals between them.
so
So
figure 1
figure 1 sketches
register
the registered number of pulses using detectors A and B,
you and
blue and red respectively. Let T be the time interval
between the
between the pulses and
OD
tau D,
and tau.
and tau D be the detector response time. Choose the correct option in regard to relation between T and tau D.
So
So
here
here,
blue curve
blue curve, that is A,
it is
it is showing the
sharp
sharp peaks
at every
at every integer multiples of
peak,
T.
whereas
Whereas
red
red curve
B
B
shows a
shows a constant response.
there are no
There are no peaks.
so it
So it means
the blue
the blue curve shows the
well
well separated peaks, that is aligned with the photon
pulses
pulses,
that is
that is detector A
can this
can resolve
individual
individual photon arrivals,
that is
that is tau dA
is lesser
is
than
lesser than time. That is
response time
response time is much
than
smaller than the
pulse separate.
pulse separation.
Whereas
Whereas
for B
for B,
tau D
tau dB is
very
very
the
so the option last.
so
So for
if
if
if the
if the detector response time is
smaller than
smaller than the pulse separation, we can well resolve
the pulse
the pulses,
the peak
the peaks,
and
and
so
so
detect
detector
A can
A can resolve the individual peaks. That's why
the
the
response
response time is lesser than the
photon
photon
interval
interval.
and
And
in case
in case of B, the detector response time is large.
next is
Next is generalized coordinates QT and PT are equivalent to the
position
position and momentum of the classical
harmonic.
harmonic oscillators.
Next
The
is
X1 and X2 quadrature of the field correspond
to
to
the
the
dash
dash and dash of the time independent electricity. So we saw that they are having the phase
of
difference of the
pi by
pi by 2, that is sine and cosine.
so it's
So X1 and X2 are the quadrature of the field corresponds to
time.
the sine and cosine of
I mean
time independent electric field.
the next
The
is
next is
The
The
next
next is you can see that we have the two phasor diagrams.
we have the two
We have the two phasor diagrams
A and
A and B,
X1 and
x1 and x2,
and then
and then we
correspond to that
correspond to that we have the four figures
with
with the
on the X
on the x-axis
axis
there is time,
on the Y
on
axis
the y-axis is
is
electric field. So
the
we are given the quadrature
so
field.
now the
So now
question
the
asking
question is asking,
match the phase
match the
diagram
phasor diagram
this
A with this
corresponding field
corresponding
profile and
field profile and identify the time of
squeeze state. So we
squeeze
have
state. So
two
we
types
have
of
two types
squeezing.
of squeeze
Either
state. Either
it can be
it can
squeezed
be
in
squeezed in
phase or
phase or it can be squeezed in amplitude.
so first
So
of all
first
we
of
are
all, they're
asking
asking
E.
about A.
So we saw
So we
that
saw that
if it is
if it's squeezed in x2,
if the delta
if the delta x1 is lesser than 1 by 2,
and the
and the x1 sorry
delta
and
x2
delta
is
x2
greater
is greater than 1 by
than
2, then
it
it
corresponds to the
corresponds to the
first curve
first
that
curve,
is the
that is the
phase squeeze.
phase squeezed.
Okay.
Okay.
Then
Then
next question
next
is
question is
B.
for B.
For
So for
B
B
is
is
delta
delta
x2
x2 is
delta x
delta x2
to
corresponds
the
to the
delta x
delta x2 corresponds to the
fourth
fourth
position
position, that is
amplitude
amplitude squeezed.
and the last
And the last
is
question is
number phase
number phase uncertainty
relation.
relations tells
It is
that
not
it is not
possible
possible to the know
the photon
the photon number
and
and the phase of wave with perfect precision at the same time.
given
Given below are the two statements in
regard
regard to number
to
phase
this.
relationship.
So the
So the
first
first
is
statement is saying
the
that the
phase of
phase of a
high
high intensity laser beam can be precisely measured.
the
The
second
second statement is exact number of photons in a sub-Poissonian light can be measured.
so
So
if
if
photon
photon number is well defined,
phase
phase becomes
highly
highly uncertain.
we know
We know this.
delta
Delta and
delta
delta phi
is great.
is greater than 1 by 2.
Okay.
Okay.
So
So
if we
if we have a high intensity laser,
that
that implies that
last
large number of photons.
if there is
If there is a large number of photons, obviously we can
defined
define the phase precisely, or we can consider delta n by n bar, that is the relative number of fluctuations
that
that decreases,
and
and
phase
phase can be well defined.
so the
So the statement
S1
S1 is true.
about
About the second statement, if we have the sub-Poissonian
light
light,
means
means fluctuations
are
are reduced
below
below short noise,
then
then we can,
if
if fluctuations are lesser,
is
it is
below
below the
short
short noise,
exact
exact number of
what
photons
can
can be
come
counted.
If there are,
If there are large number of photons, that is G2 is greater than 1,
then
then only we are not able to
then
then we are not able to identify
the
the
we are
we are not able to count in
engaged
case of
for
poisonian or
super
super poisonian. When we have the chaotic light, then we will not be able to count the exact number of photons. But in case of sub poisonian,
the
the
fluctuations
fluctuations are
reduce.
reduced,
So we
so we can
define
define the
count
count the
the
exact number of photons.
okay.
Okay, so this was all about today. So we
Yes.
discussed the
First of
first
all,
of all
we
we
define
define the
the
G2
coherent
coherent
state,
states, then we considered the light
electron,
electromagnetic waves as a quantum harmonic oscillator, then we related
how can
how can we represent EM
we
wave in terms of phasor diagram, we related with the analogy of
x1
x1 and x2
in
in
terms of
terms of Q and P,
and
and then what are vacuum fields,
then
then
vacuum
vacuum
0
zero point energy,
and a
and a
brief
brief intro about
squeeze.
squeeze states.
So we
So
will
we will continue about
squeeze.
squeeze state in the next lecture.
So
So
thank you.
thank you so much.